Good morning everyone. So today we are going to start a new chapter, inclusion exclusion. We will initially see the concept of inclusion exclusion using the concept of Venn diagram, and then we will generalize it in the next section. So to begin with, let us assume that there are 100 students. So total number of these students are 100. 50 students are taking French and 40 students are taking Latin, and 20 students are taking both of them. How many students take no language? So if F represents the number of the students which are taking French, it means F bar is the number of the students which are not taking French. Similarly, L bar is the number of the students which are not taking Latin, and that's why the number n F bar intersection L bar gives you the number of the students taking no language. Now using De Morgan's law, this would be equal to F union L whole bar, which would be equal to total number of the students minus n of F union L. Now if I compute F union L, so since it is F and L, so if I write n of F and n of L, you will realize that if you see even the Venn diagram, then this part which is F intersection L is counted twice, in n of F also and n of L also. Therefore I should subtract it because it is counted twice, and this gives me the n of F union L. That gives me F bar intersection L bar is n minus n of F minus n of L and plus n of F intersection L. So I have all the data now. So 100 minus 50 minus 40 and plus 20, that gives me 30 as the required answer. Now the quick observation is that this formula is a two-set version of general n-set inclusion exclusion formula, and we call it an inclusion exclusion because it includes whole set n, then exclude single sets, and then include two sets. So include, exclude, and so on. Now using inclusion exclusion formula, let's try to solve this problem. So how many arrangements without repetition of the digit, all the digits 0, 1 to 9 are there, in which the first digit is greater than 1 and the last digit is. So if I have to use the inclusion exclusion formula, then it says that n of A bar intersection B bar is, and then you have the right hand side. It means here AND is there, which represents the intersection. So my A bar is first digit is greater than 1 and B bar is last digit less than 8. It means my A is first digit is 0 or 1 and B is last digit is 8 or 9. So now if I compute n of total n, so total n would be 10 factorial because 10 positions are there, 0, 1, 2 till 9. Each first one is filled in 10 ways, then 9 ways and so on, because repetition is not allowed. Then if you compute n A, then the first position is filled in 2 ways and the remaining in n factorial ways. Same is about n of B. And if you compute n of A intersection B, it represents the first and last positions are filled in 2 ways, two ways. It means the remaining positions are 8, which can be filled in 8 factorial ways without repetition. And that's why your n of A bar intersection B bar is 10 factorial minus 2 times 9 factorial minus 2 times 9 factorial plus 2 cross 2 cross 8 factorial. Now if I have to introduce the inclusion exclusion formula for 3 sets, I just generalize the concept of 2 sets. So n minus n of F L G then the addition of intersection of FL, LG and FG, and then the subtraction of F intersection L intersection G. Now let's try to solve this problem. It says that how many ternary n-digit ternary sequences are there with at least one, at least 1 0, at least 1 1 and at least 1 2. So again you can see there are 3 sets are there. Yes. So now if I see in terms of A bar intersection B bar intersection C bar or n of A1 bar intersection A2 bar intersection A3 bar, then my A1 would be no 0, A2 would be no 1s and A3 would be no 2s. Yes, total n is simple, 3 raised to the power n, because n positions are there, each can be filled in 3 ways. Then n of AI is 2 raised to the power n. For example, no 0 is there, so you need to fill with 1 and 2 only. N of AI intersection AJ. So if I see n of A1 intersection A2, it means no 0s and no 1s, so only 2s are there. So if I have to fill all the position with 2, then it can be done in only one way. And n of A1 intersection A2 intersection A3 is 0, because there is no sequence with no 0, no 1 and no 2s. And now if you substitute the values, then n of A1 bar intersection A2 bar intersection A3 bar is 3 raised to the power n minus 3 dot 2 raised to the power n plus 3. The next part says that how many ternary sequences with at least one void, so one missing digit. So missing digit means 0 can be missing, 1 can be missing or 2 can be missing, but it is also possible both 0 and 1 are missing. It means that I am looking for A1 union A2 union A3. A1 represents 0 is missing, A2 1 is missing, and A3 2 is missing. This is total n minus, using De Morgan's law, n1 bar intersection and A2 bar intersection A3 bar, which we have just computed. So this gives me the required answer. Now this is the question which you cannot solve it using generating function or using recurrence relation. So how many positive integers are relatively prime to 70? For example, 9 and 70 are relatively prime, 11 and 70 are relatively prime. It means which have no common divisors with 70. Yes, so we can see it like this, that let u be the set of integers between 1 and 70, then the prime divisors of 70 are 2, 5, 7. So relatively prime means which are not multiple of 2, 5, 7. So A1 bar is not multiple of 2. Similarly, I can define A2 bar, A3 bar. It means n of A1 is the multiples of 2. So multiple of 2 are 35. N of A2 are multiple of 5, which are 14, and n of A3 are multiple of 7, which are 10. Similarly, I can write down n of A1 intersection A2, which is multiple of 2 and 5, which means multiple of 10. So there are 7 multiples of 10 till 70. N of A1 intersection A3, multiple of 2 and 7, which means multiple of 14, which are 5. And A2 intersection A3, multiple of 7 and 5, which is multiple of 35, so which are 2. Yes, and the multiple of 2, 5 and 7, which is 70 only, intersection A3, so which is 1, there is only one number. Now use the inclusion exclusion principle, that gives you n of A1 bar intersection A2 bar intersection A3 bar is 24. So this is the last question. If you look at this question, then and if you try to solve it using inclusion exclusion principle, you may observe that many of the details are missing. It cannot be addressed easily using an inclusion exclusion principle. Then how do we solve it? So to solve it, I should introduce the concept of Venn diagram. So there are three cases: learning French, Latin or German. So if you see the Venn diagram, I partitioned it into the 8 areas, and what I am looking for the numbers in area 3, because this is the students taking all 3 languages, and n of 8, which is the exterior region, is taking no language. Yes, which means not taking French, Latin and German. Now let's see what information about have. Do we have n of 1, n of 2, and we need to compute all of them. So the first information is 20 students are taking French, 20 Latin, 15 German. So it means that n1 is given, n5 is given, n7 is given, and 10 are taking French and Latin. It means n2 plus n3 is given. Yes. The next information is 40 are taking French. It means that 40 is the sum of 1, 2, 3, 4. So sum of 1, 2, 3, 4 is 40. And I have 1, 2, 3 information. So I can compute n of 4, which comes out to be 10. Similarly, 40 are taking Latin as well as 40 are taking German. So 40 are taking Latin. So Latin is 2, 3, 5, 6. 2, 3, 5, 6. So 2, 3 is already given, 5 is already given, 6 we can compute. Similarly, last one is the German, so which is 3, 4, 6, 7. We have just computed 4, 6. So using the information I get n3, which is the one information I required. But now you can see that I have all the information except n2, but n2 plus n3 is 10, so that gives me n2 is equal to 5. Now I have all n1, 2, 3, 4, 5, 6, 7, so n8 would be, out of total I subtract, so total is given 100 student, I subtract it, which gives me n8 is equal to 50. So in the next class we will cover more questions on inclusion exclusion principle.